the naming is I2C bus. Actually 2I, that is why it is I2C. It is called inter-IC bus. And this is another bus. In our last lecture we have covered control area network bus. The difference between these two buses is that we are studying embedded systems, and control area network bus is applicable for large scale embedded devices or embedded systems, likewise automotive vehicles, aerospace, and maritime ships. So these are very large scale embedded systems, but oppositely inter-IC bus is applicable for small scale embedded devices. So we are covering both of them, and CAN protocol is already covered, and today we are studying inter-IC bus. This is the lecture reference, and in this lecture I hope to cover these topics. Similar to CAN bus, we will learn here what is inter-IC bus and for what purpose we should use for. The bus characteristics, some features. It has its own protocol. Likewise, in CAN bus, just a minute. Okay, sorry. In CAN bus, we have a protocol that is divided into 3 layers: physical layer, protocol layer, and message filtering layer. Here as well, we have to follow some specific rules that is defined by the protocol, and it is called inter-IC bus protocol. In addition, we have the data format, and we learn about what devices uses inter-IC bus. We'll see that, and we'll see that examples. So what is inter-IC bus? As I mentioned, that taking the 2 I's of this I and this I, these two altogether defining that I square and inter-integrated circuit bus. And it is also a small area network that actually connects ICs and other electronic components in a small scale embedded systems. And why we are saying this is a small area network? Because whether it's a CAN bus or inter-IC bus, both of them are CAN means control area network, and it is also a small. Inter-IC bus is also applicable for a small area network, because in an embedded system, the bus connects multiple components of that embedded system. So that is why we say it's a small area or large scale network, and where the components of the embedded devices, likewise the ICs, interacts or communicates with each other and exchange data. But it is not not typical our computer network oriented data communication. Rather, control information are exchanged in the embedded devices. Okay, so today a variety of devices are available with inter-IC bus. These all are a small scale, where in the microcontroller, in the EEPROM, real timer, interface chips, LCD driver, AD converters, these all are designed in a printed circuit board. So a single chip is designed in a single board or in a printed circuit board. Those are connected via inter-IC bus. And the inter-IC bus, unlike CAN bus, it is synchronous. The data are exchanged between the components of the IC or of the on the chip. The data are exchanged synchronously. So as it is synchronous, serial signal are exchanged. So we need one wire for exchange the clock information, because synchronous means at the same time, and to maintain the same time, all the ICs maintain the same clock information. So that is why clock pulses are needed to be available to all the ICs. So here as well, we need one wire to exchange the clock pulses, and another wire will be used to exchange the data. So in this bus, we have two specific wire, one for clock information and one for data. And the two wires carry information between a number of devices. Okay, next. For what purpose we used, I will show you. But the data it is basically used for data transfer between inter-ICs or ICs, integrated circuits, and systems at relatively low rates. And you can see it has three modes: the classic mode, fast mode, and high speed mode, and with variety of speed limit. In CAN bus, the maximum speed we can achieve is 1 Mbps within a length of 40 meter. But in this case, the classic that can achieve 100 kbps, the fast mode can achieve 400 kbps, and the high speed mode can achieve maximum 3.4 Mbps, megabit per second. Now, what advantages we are getting by using the inter-IC bus? First advantage is that it reduces the board space. That is the printed circuit board. The size of the printed circuit board is reduced due to the use of this. And also, as the printed circuit board is reduced, the cost is also reduced. And specifically with these 3 points, we can explain how the board size is reduced and how the cost is reduced. It allows the ICs with fewer pins and smaller packages. So that is why the board size is reduced. And as we are having smaller pins, smaller packages, so obviously the connectivity complexity can be avoided. And also it allows digitally controlled components to be located close to their point of use. So in a small scale printed circuit board, multiple ICs can be interconnected by using the inter-IC bus. Now, likewise, in CAN bus, we have seen that electromagnetic interference can hamper the data transmission, EMI. We have seen that in CAN bus. But in inter-IC bus, as the distance is small, it maintains a small distance in a single printed circuit board. So the noise or electromagnetic interference are negligible, can be considered negligible in inter-IC bus. It is not zero, but it is negligible. Then about the inter-IC bus characteristics, already I have mentioned it uses two wires, one for timing specifications and one for data. And the clock, it is a serial bus. That means bit by bit the data are exchanged between the ICs. So two wire we use in this bus. One is serial data and another is clock. So serial data is called SDA line or SDA wire, and the other is SCL, serial clock, that is the SCL. Though it's a synchronous, but we should have a start and stop condition, not start and stop beat. In asynchronous, we use start flag and end flag, or start beat or end beat. But in this case, we have a condition of start and stop, not start and stop beat. So in inter-IC bus, the start condition and stop condition are controlled by the clock pulse. I will show you while I will talk about the clock pulse. In this case, the start condition and stop condition are maintained by the clock pulses. Okay. Now, all the devices are categorized in this bus into two categories. One category we say, one category is master category device, usually microcontroller or microprocessor devices, microprocessor unit or microcontroller unit becomes the master device, and with that some likewise the AD converter or the LCD driver or some other integrated circuits, those are these two or those are categorized as slave devices. So we have some master slave relationship in this CAN bus. So let's say this is our wire, this is our wire, so this is our SDA serial data wire that connects these three devices, and let's say we have clock pulses that also connects by these devices. So you see that who is the master here? This is the master device, and it generates all the clock pulses via the SCL line, and it also selects the slave addresses to select a particular IC. So the slave selection protocol uses a 7-bit slave address. That means in total, in a single printed circuit board, we may incorporate 2 to the power 7 numbers of ICs. So total 120 ICs can be connected in a single inter-IC bus or in a single printed circuit board. But if it also allows an extension to 10 bits. Likewise, in CAN protocol, we have seen the identifier value is 11 bit, but in the extended version, the identifier value they have used 29 bit. So similar to that, as it is a small scale bus, so we have 7-bit slave addresses. That means 2 to the 7 numbers of slaves are possible, and it can be extended up to 10 bits. It can be extended up to 10 bits. Next, bidirectional data transfer. Bidirectional means the master can send the data to slave and slave can send the data to master. So bidirectional data transfer is possible, and of course after sending each byte there will be an option of acknowledgement by using the clock pulses. So here clock pulse plays a vital role for making the communication successful. And there is no fixed length of data transfer. In CAN, if you can recall, in CAN we have 8 bytes of data in a single data frame. But here no fixed of data, but after sending each byte, there should be an acknowledgement or negative acknowledgement signal that is to be maintained based on the clock pulses. So as a summary, if I say the difference between CAN and IC, inter-IC bus, CAN is for large scale, inter-IC bus is for small scale. CAN maintains asynchronous communication. Serial data is transferred, but asynchronous communication with a start flag and end flag. But inter-IC bus maintains a synchronous communication, but here we should have a start condition and a stop condition. In case of CAN, the number of nodes identifier can be identified by 11 bits or 29 bits in the extended version. In inter-IC bus, we have a 7-bit slave addresses, or it can be extended up to 10 bits. And we have a category of, we don't have any category of nodes in CAN bus, but in this case, we have a category of master and slave. And in CAN bus, we have a maximum data length size 64-bit or 8 bytes, but there is no fixed length in case of inter-IC bus. Okay. One exceptional is that I have shown you the assumption that a single master and multiple slaves. but there might be a possibility of multi-core system. In case of multi-core system, you are already familiar with multi-core processor. In a system, multiple processor or multiple microcontrollers are present. In that case, we have a situation of multi-master possibility. Yes, multi-master is allowed in inter-IC bus. In that case, who will control, that is defined by some arbitration procedure. Likewise in CAN bus. In CAN bus, you have seen the arbitration procedure. Similar to that, in a multi-master inter-IC bus, we have the clock synchronization as well as some arbitration procedure who will act as the master. So that is defined by the arbitration procedure. We have already seen the transmission speed in 3 categories, and we have some registers, and of course in this inter-IC bus is compatible to work with different IC technologies. IC technologies means there is a course like VLSI. In VLSI, different sorts of IC technologies are taught. So we mean that IC technologies may vary from manufacturer to manufacturer, or from technological development, it might be changed. So inter-IC bus is compatible with different categories of IC technologies. Now let's proceed. First of all, if we can see the figure of a inter-IC bus. So let's see, this is the inter-IC configuration, then I will come to the node categories. So inter-IC bus configuration, in inter-IC bus configuration, you can see that we have 2 microcontrollers. For time being, just omit the second one. So I am not talking about, I will talk about the multi-master concept at the end of this lecture. So for time being, you just consider we have a single master and we have these slaves. So gate array, AD converter, LCD driver, static RAM or EEPROM. So these are separate ICs. These are separate ICs. We are telling those as node or component. This is also an IC. Microcontroller is also an IC, but it is the master node, and these all are slave nodes. And these slaves have the ID, and that ID is represented by 7 bits or can be extended up to 10 bits. Okay. Now you have got the idea of master and slave. Now what a master can do and what a slave can do. Let's see. First of all, the master node. Master node is the main node to control the inter-IC bus operation, and it generates the clock pulses. This is the main task. So using the SCL line, you can see using the SCL line, this is not loop, this is not circular bus. You can see there is a cut here. So it's a, you can say it's a bus, it's a bus topology you can consider. So we have the SCL, and through this SCL, the clock pulses are available, and who provides that clock pulse? The master node. So the master node generates the clock pulses. It initiates a transfer by generating the start and stop condition. Through the clock pulses, it initiates, based on the clock pulse, it initiates the start and stop condition of the data. It transfers the slave address. So the master selects with whom it should communicate, or to whom it should send the data, or from which slave it should receive the data. So everything is controlled by the master. The master transfers the slave address. Suppose if the master transfers the slave address of LCD driver, then the master will inform him, okay, I am selecting you, please receive my data. So now it will send the data through the SDA line, and also it will send the slave address through the SDA line. Similar to that, if the master likes to receive any data from the LCD driver, again it should select the LCD driver by providing the slave address, and afterwards the slave will send the data to the master through the SDA line. And it means the master determines the direction of the data transfer. So whether the master is sending to slave or slave is sending to master, that is determined by the master node. And in case of the second category, that is the slave address or slave nodes, slave doesn't have any power. It only responds only when it is addressed by the master. So if any slave node is selected by the master, only then it interacts, whether it receives the data or it can transmit the data. And it follows the timing that is controlled by the clock line. It always, its timing is controlled by the clock pulses that is available in the SCL line or SCL bus. Okay, so I think you have a brief idea about the inter-IC bus. Let's proceed with some more details. Okay, the inter-IC hardware details. In inter-IC hardware details, already you have got the idea of inter-IC bus and some basic idea about the master node and the slave addresses. But the electrical components, that means the signaling, can have a maximum amplitude or voltage of 5 volt, and it uses some pull-up resistors so to ensure the 5 volt current. And at any given moment, the inter-IC bus can have either of these three states. So let's see. So this is the electrical aspects. We have two pull-up resistors, and here is our data line SDA. Here is our clock line SCL, and this is device 1, IC1. You can consider this is IC2, where the data can be received, the clock pulse can be received, and the data can be transferred, and the clock pulse can be transferred. Because device 1 and device 2 we didn't mention about the who is master and who is slave. So based on this, at any given moment, the inter-IC bus state can be defined in 3 categories. One category is that no one is transferring anything. The bus is idle. That means it is the quotient mode or state, that is the idle mode. Or the bus can be in master transmit mode. That means the master is transmitting. That means master likes to transmit any data to static RAM. So master is in the transmit mode. Or if the master asks the static RAM to send any data to microcontroller, in that case the master is in the receive mode. So every time you have to think about from the master's reference point of view, or the microcontrollers or microprocessors point of view, the node that is the master, always think of it. So based on if the master is idle, the bus is idle. If the master transmit anything, the master is in transmit mode. Or through the bus, if the master receives anything, master is in receive mode. So this is the hardware details. And the electrical aspects. Regarding the electrical aspects, another thing I have to add, the inter-IC devices are wired and ANDed together. And what is wired and ANDed? That I have already mentioned in your control area network bus protocol operation. That means if any device sends any zero signal or logic low signal, the bus will be in the dominated state. Otherwise, if every device sends a recessive signal or logic high signal, the bus is in the recessive state. So it means that any single node writes a 0, the enter line is 0. Or if every device sends a 1, logic high signal. In that case, the interbus is in the recessive state or idle state. That is the wide end mechanism that we have already learned in CAN bus protocol. Now I'll talk about the bit transfer on the inter-IC bus. So first I will show you that in normal data transfer, the data line only changes state when the clock is low. Okay. So as we know that the SDA, this is the data line, and the SL is the clock pulses. So you see, here we have the clock pulses. Here we have the clock pulses. This is one clock pulse. This is one clock pulse. This is another. This is, and dot dot dot. It is continuous. Now, that if any transition needs to be made, so the data in the data, that transition always needs to be made when the clock pulse is in the low state. You see, in normal data transfer, this is a thumb rule. This is the protocol rule, and we are learning the protocol of inter-IC bus. This is the rules that if any data, that means your current data is 1. If you like to make it 0, make the transition when the clock pulse is in the low state. Or if your data is 0, if any device's data or IC's data is 0, there is a transition that we have a 0 data and next transition is 1. Next data is 1. So that one should be made while the clock pulse is in the low state. So now the data is 1. So any sort of, for data transfer, any sort of change in the data has to be made when the clock is in the low state. This is a thumb rule that inter-IC bus follows. Have you got it?
Yes, sir.
Okay. Now, next, I have already mentioned that we have the stop bit and start bit. And start and stop bit is maintained with the help of the clock pulse. Suppose if a node, that is whether that is a master or that is a slave, in either direction the data can be transferred. But if the slave transfer anything, that is selected by the master, or if the master sends anything to slave, that is also selected by the master. So in either case, for data transfer, the start condition and stop condition are mentioned when there is this is the start condition. How we are defining the start condition? You see, the start condition means there should be a transition from high to low, but at that time the clock pulse should be in the high state. There should be, for making the stop condition, there should be a transition from 0 to 1 or low to high, and at that time the clock pulse should be in the high state. So you see, this is another thumb rule. If in case of data transition, if the data transition in the earlier slide of what we have seen, in case of data transition from 0 to 1 or 1 to 0, whatever the condition is, the clock is in low state. But for start condition and stop condition, the start always maintained for one byte data. Say from 1 to 0, the transmitter or the sender, whether M or S is the sender, doesn't matter. If M sends anything, it should start the data making a transition by 1 to 0, and at that time the clock pulse should be in the high state. then it will maintain the data transfer 0 1 1 1 1 0 0 0. So this transition, in this transition 1 1 1 doesn't matter, but 1 to 0, in this case, of course, the clock pulse should be in the low state. So this is the in between rule. That rule is data transition rule. But for a stop condition, again for a stop condition, the data transition should be 0 to 1 in the data line, and at that time the clock pulse should be in the high state. So these are the two rules. Yes.
Sir, when we are doing data transmission, let us assume that the last data was 1. So after 1, if we want to stop, how do we get to 0?
Okay. In that case, let's say our data is 1.
Yes, sir, the last data.
Our last data is 1. So, but you have to make a 0 to 1 transition. So in that case, you have to use extra cycle or extra clock pulse. You know that we have our data is 1, and after that, if we make a transition, we have to make a transition, and at that time we should make a low in clock line.
Yes.
In the clock line, so we are getting there. Then whenever the clock will be in the high state, we will move to 0 to 1. So obviously,
yes,
this condition is maintained. You see?
Yes, sir.
Your data
is extra 0 that we used. It's not a part of the data.
It is not a part of that data.
Okay, sir.
Okay. Okay. So we have defined the start condition and stop condition. Okay. And next, I'll talk about the addressing, and then I will talk about the first byte, second byte, and these are the things I will talk about. Okay. Okay, another declaration is that you guys are facing problem with the saving in Proteus. So today I will take 10 minutes to show you that I have found some solution, and I will, as your section is only one section in the lab part as well. So I will take 10 minutes from the theory part, and I will not take the whole 2 classes at once. I will finish it, so I will not give any break. And the section 2 is a bit lagging behind in the theory, so that is why I will not complete this lecture today full. So let's see how long I can go. It's 3:05, right? Okay, 35 minutes we have taken for the class. So let's say at least 50 minutes first I will complete. Then I will move to the lab instruction. I will take 10 minutes for the lab instruction. Okay. So I have defined about the bit transfer, the transition of bits, as well as the start condition and stop condition of the data. And in between the data, we should have the maximum. After each byte, we should put a acknowledgement or negative acknowledgement. Okay. So before understanding the acknowledgement and negative acknowledgement, before understanding the data transitions, I'm clearing the addressing part. So each node has a unique 7 or 10 bit address. The 7 is the basic inter-IC bus, and 10 is the extended version of the inter-IC bus. And peripheral often have fixed and programmable address portions. Addressing started with either 4 zeros or 4 ones. These are special functions, and the special functions are maintained here. That for it's a general call address, this is a null address, some extension, address extension. With address extension can be used by putting an extra 4 bits with 1. In the next, this is the next byte of the actual address. So in total, you can use 10 bits. You can consider 10 bits. So these are the special cases. But just for time being, to understand the inter-IC bus, we consider the 7-bit address. So you see, this is our 7-bit address. So at the very beginning of your data transition, this is also data. The 7-bit address is also part of the data. And who tells this? the master tells this. The master informs, say this is our master and this is our slave 1, this is our slave 2 and this is our slave 3. And these are circularly connected via the inter-IC bus. And it has 7-bit address. It has 7-bit address. So everyone has 7-bit address. So for time being, let's consider that M is selecting S2. So what M will do, M will send the 7-bit slave address of the S2 in which line? In the SDA line. So whatever the 7-bit address, slave master will inform. And in the next bit, the master will say that whether the master is likes to transfer or the master likes to receive, that is written by either write operation or read operation. So if the master he writes 0 here, means slave written to by master. Slave written to by master means the master likes to write some data to slave. That means who will send? Master will transmit. And the oppositely, if 1 is put in this field, that means the address that is provided here, to that address or from that address, the master will receive. The master will receive or the master will read the data from that slave device. And after that, after getting the address and after getting this instruction, the slave will send the acknowledgement. So this is a basic fast byte data transfer on the inter-IC bus. For having each data communication or for having each data transfer, this is a must. This is a mandatory fast byte in the data transfer using the slave address. The master provides the slave address. Master is informed whether the master likes to read the data from the slave or the master likes to write data to the slave. That is informed in the first byte. And after that, 1 bit of data transition will be made through SDA line. And in that case, the slave will send an acknowledgement signal. How? Let's see. Okay, so one thing is that the connections in inter-IC bus, the master can do 2 things and the slave can do 2 things. So first of all, what a master can do? A master can be a transmitter only, or a master can be a transmitter and receiver as well. And on the other case, a slave can be a receiver only and a slave can be a receiver and transmitter. Can anyone make these sentences clear to me? Can anyone of you? Actually, this is the last slide I will cover and this is the last slide I will cover. Then after that, in the next class, I will finish the rest of the slides. These things up to this, I will cover. Can anyone tell me that master can be transmitter only and master can be transmitter and receiver, and slave can be receiver only and slave can be...
There is acknowledgement present, then in the case there will be transmitter and receiver required. Otherwise, only transmission and receive. I think so.
Okay, just connect these 2 together. And connect these 2 together. Okay. When master is the transmitter only, that means master likes to send any data to slave. So master is transmitting, slave is receiving. Simple. This is the first case. This one.
Yes.
And in the second case, master is asking, hey, send me the data. And master moves to the, master is asking, hey, send me the data. So it is while it is asking, it is in the transmission mode and slave is in the reception mode. You see? Okay. And asking by what? Asking by the 7-bit slave address. Read or write? Read. So this is the 8-bit. Okay, read. It is asking, send me the data. So the slave is in the receiving mode, master is in the transmitting mode. Okay, and just after that, the slave will be in the transmitting mode and master becomes in the receiving mode. Have you got it? This is in the acknowledgement section. And after sending the acknowledgement by this way, the slave will start sending the data of 1 byte, 1 byte, 1 byte, 1 byte. This is how, as long as it has data towards for the master. Have you got it?
Yes, sir.
Okay. So up to this, I'm okay. No, I can take two more slides. It's okay. Should I? Let's see. Let me see. Okay, I will move with acknowledgement in the next class, as because I will now show you something from the lab. So up to slide 16, I am covering, and for section 2, actually I have covered up to this. For section 2, I have covered up to this today, up to slide 9. So I like to move together for both the sections. So that is why today you get some benefit. But I like to use the time for 10 minutes for your lab purpose. Okay, first complete it. Do you have any question regarding the inter-IC bus, the part I have covered today? Any question? If no, then I'm moving to the lab. I hope that every one of you have gone through the video lecture I have given in your last lab, where you might have, here is my Proteus. Is my screen shared with you? My desktop, can you see that? Okay. Okay. So as we are facing the problem of saving the file, so I got some shortcut. Actually, I have to go through some blocks and many things. Then I found this as a shortcut, that whenever you open one untitled Proteus 8 professional homepage, and we should, from the menu bar, we should create one schematic capture. Okay. So this is our schematic capture, and just after opening the schematic capture, you just press the save button. If you don't do this, if you include any component like 8086, like 8255 PPI, like the latch or any peripheral like LED or 7-segment display, then the problem starts. In some cases it starts early, in some cases it creates later. So what you should do at the very beginning, you should create, so let's say my project name is first. If you create, I've created in the desktop, and you see my file is created. Even if I close it, no problem. Again, my file, I can open the file. You see, and then afterwards you start working. So how we should start? We should start our work. At first, we should pick a device, and step by step we will do that. 8086, search it, include it into the device list. Next, 8255, 8255A, So include in the list. Let's say 74AC373 our latch that we use. Include that. Then let's say we have a LED that in your lab that we have used. Okay, animated bicolor LED model, red and yellow. So I have taken that, and then these are the components in your third lab I have used. Let's see that how you can include. Click one, include one. Is it visible?
Yes, sir.
Okay. Now click latch, include that. Okay, fine. Next, click the 8255, include that. Click the LED, include that. Let's connect it. Okay. I have connected it. Let's say I'll not show you everything. Just let's say I have connected the latch, and these are the instructions I have given in your video file. Then after that, save it, close it. This is the problem. Save it, and no. Let's see. Okay, so again, in some cases it creates the problem. Again, you see now it's blank, right? Now it's blank. But in some cases, okay, let me check another file. So this is also this problem. But in some cases, I have found that it can be saved. Oh my God! Again, I have got some clue, and
স্যার আমার কিন্তু স্যার সেভ হচ্ছে ওই আপনি যে ফাইলটা ফার্স্টে দিছিলেন ওইটা
গতকালকে আমি সেভ করছি। গতকালকে এই ক্লুতে আমি সেভ করছি, কারণ আমি একটা ব্লগ থেকে এই ইনফরমেশনটা পেয়েছি যে প্রথমেই ফাইলটা ওপেন করে ফাইলটা ক্রিয়েট করে সেভ করে রাখতে হবে, তারপর আমি বারবার সেভ বাটন চাপ দিলে আমার সেভ হয়ে যাবে। তোমার কি সমস্যা বলো?
স্যার আমার সমস্যা হয় না, মানে আমি নরমালি সেভ করতে পারছি, আমার কোনো মানে এত।
তুমি কি এই ভার্সনটা ব্যবহার করছো?
এই ভার্সন না স্যার, মানে
আমারও সেম। আমি আলাদা একটা ভার্সন থেকে ইউজ করতেছি, ওইটা সেভ হচ্ছে 8.9 তে। 8.9
এবং এইভাবে স্কিম্যাটিক ক্যাপচার ইউজ করে সেভ করা যাচ্ছে?
আমি স্কিম্যাটিক না, আমি নরমালি সেভ করছি, জাস্ট ফাইলটা সেভ এস দিয়ে সেভ করেছি।
আচ্ছা ওকে, তাহলে আমার সাথে একটু দেখো তো শেয়ার করা যায় কিনা। আমি কিন্তু গতকালকে এই ভার্সনটা দিয়ে সেভ করতে পারছি, এবং আজকে সকালে ওদেরকেও ল্যাব দেখাইছি, আমি রান করেই দেখাইছি ল্যাব। আচ্ছা এক মিনিট আমি আরেকটা জায়গা থেকে একটু দেখবো, আমার ফাইলটা আরেকটা ফাইল আমি দেখবো একটু, জাস্ট a minute. Lec13. This is the Lec13. So you see, আমি এটা Lec13 সেভ করছি গতকালকে, এবং এইটাই তোমাদেরকে আমি টাস্ক দিয়েছিলাম, রাইট? এইটা আমি গতকালকে সেভ করছি। তো এটা সেভ করা যায়, কি জানি সমস্যা হচ্ছে, মানে মাঝে মাঝে সমস্যা করছে, বাট কখন করতেছে এটা বুঝতে, এটা আমি প্রথমেই কালকে ওই ক্লুটা পাওয়ার পরে প্রথমেই করে নিচ্ছি। এনিওয়ে, তো তোমাদের যাদের যে ভার্সন দিয়ে সেভ হচ্ছে, তাহলে সেই ভার্সন দিয়ে তোমরা একটু নিজেরা শেয়ার করে এই ফাইলটা আপলোড করবা ইনশাল্লাহ। ওকে
স্যার, আরেকটা প্রবলেম সেটা হলো স্যার কম্পিউটারের উপর ওই ফ্রিকোয়েন্সিটা আর কি ডিপেন্ড করতেছে। তা
এখানে একটু দেখাই। ওকে, আমি একটু এখানেই দেখাই।
স্যার রানটা একটু স্টপ করো।
ও সরি। ওকে, তোমাদেরকে একটু বলি, আমাকে দুটো প্রশ্ন আমাকে আগের গ্রুপ করেছে, তোমাদের কাছে ওইটা ক্লিয়ার করি। যেহেতু ল্যাবের ব্যাপারটা সেদিন আমি শুধু ভিডিও লেকচার দিয়েছি তোমাদেরকে, ল্যাবের ব্যাপারে একটু বলি। প্রথমত হচ্ছে আমরা বাইনারি ফাইল নিয়ে কাজ করতেছি, সো ইমুলেটর 8086 দিয়ে যখন আমি ফাইলটাকে সেভ কম্পাইল করছি তখন অটোমেটিক বাইনারি ফাইল তৈরি হচ্ছে। হ্যাঁ, তুমি যেখানেই রাখো না কেন, যে ডিরেক্টরিতে রাখো। আর ক্লক স্পিডটা কেন কমাই দিচ্ছি কেউ কি বলতে পারবো আমাকে? ওয়াই উই আর রিডিউসিং দ্যাট? এখানে বাই ডিফল্ট 5 আমরা জানি 8086 5 মেগাহার্জে কাজ করে অথবা 10 মেগাহার্জে কাজ করে।
চোখে দেখা যাবে না স্যার এটা।
এক্স্যাক্টলি, আমার যদি 5 মেগাহার্জের মতো ক্লক স্পিড আমি ব্যবহার করি তাহলে আমার এই যে ব্লিঙ্কিংটা দেখতে পাচ্ছি সেটা আমরা এখানে আউটপুট হিসেবে দেখতে পারবো না। তো অ্যাকচুয়ালি আমরা এখানে ম্যানিপুলেট করে ক্লক ফ্রিকোয়েন্সিটাকে কমাই দিচ্ছি, এটা একটা জিনিস। আর আরেকটা প্রশ্ন আমাকে অনেকে করেছে, স্যার ওয়াই উই আর ইউজিং ইন্টারনাল মেমোরি? আমরা ইন্টারনাল মেমোরি করে আমরা এখানে 1 দিয়ে দিচ্ছি, কারণ ইন্টারনাল মেমোরিতে আমাকে 64 কিলোবাইট ব্যবহার করতে দেয়, মানে হচ্ছে 1000 থেকে 1FFFF এই অংশটাই আমরা ডেটা সেগমেন্ট হিসেবে, কোড সেগমেন্ট হিসেবে ব্যবহার করতে পারি। এই জন্যই আজকে একটা জিনিস তোমাদেরকে বলি যে এই জন্য এখানে দেখবা আমি শুধুমাত্র অ্যাড্রেস বাস এডিপিটা শুধু আমি ডেটা বাস হিসেবে ব্যবহার করতেছি, এখানে কোনো অ্যাড্রেস আমার 20 বিটের অ্যাড্রেস লাগতেছে না, কারণ হচ্ছে অ্যাড্রেসটা ইন্টারনাল মেমোরি থেকে আসে। মেমোরিটা হচ্ছে ইন্টারনালি এই সিঙ্গেল প্রসেসর সিস্টেম, সিঙ্গেল বোর্ড প্রসেসর সিস্টেমের এর ভিতরেই আছে। তো আমি কোনো এক্সটার্নাল মেমোরি যদি ব্যবহার করতাম তাহলে আমাকে A16 A19 এটাকেও ব্যবহার করতে হতো। এটা হচ্ছে আরেকটা আনসার। সো ওয়াই উই আর ইউজিং দ্য ইন্টারনাল মেমোরি। তো এই জিনিসটা, এই দুটো জিনিস তোমাদের কাছে ক্লিয়ার করার দরকার ছিল বোধহয়, আমি আজকে এখানে এটা ওপেন করলাম। তো এনি আদার কোশ্চেন?
হ্যাঁ স্যার, মানে আমার যেটা ফেস করছি আমি সেটা হলো স্যার, মানে 1 MBPS আমার হচ্ছে, মানে 1 হার্টসে মেগাহার্টসে আমার হচ্ছে না। তা আমি অন্য একটাই করছি, কততে আমার মনে নাই। আরেকটা ফ্রেন্ড ও দেখলাম 0.2 তে করছে। তো স্যার
তুমি 0.5 টিউন করে দেখো, 0.5 0.2 0.4 এইভাবে টিউন করে দেখো, যেটাতে ভালো আউটপুট আসে সেটা মেইনটেইন করো।
এখন স্যার এক একজনের পিসিতে এক এক রকম, তো
হ্যাঁ
ফাইলটা পাঠায় তাহলে দেখা যাবে আপনার পিসিতে ওটা ওরকম।
আচ্ছা, আমি এটা টিউন করে দেখবো, ওটা আমি যখন চেক করব টিউন করে দেখবো, সমস্যা নেই।
আচ্ছা ঠিক আছে,
ঠিক আছে। এটা একটা ভালো ফিডব্যাক পেলাম যে এক একজনের পিসির উপরে বেস করে এটা হচ্ছে। ঠিক আছে। সো আমার মনে হয় এই জিনিসটা যেটা আমি গতদিন ভিডিও লেকচারে দিয়েছিলাম, কোনো টেকনিক্যাল জিনিসটা দেখাইনি, সেটা একটু দেখালাম। আর একটা ওয়ে যদিও দেখানোর সময় মনে করলাম যে আমি সাকসেসফুল হব, বাট হয়নি। বাট গতকালকে এই ফাইলটা আমি সেভ করতে পারছি। ওকে, থ্যাংক ইউ। আশা করি সবার কাছে ক্লিয়ার। সো সি ইউ অন দ্য নেক্সট টুইসডে ইনশাআল্লাহ। আজকে এই পর্যন্তই ক্লাস নিলাম। তো থ্যাংক ইউ সবাইকে।
আসসালামু আলাইকুম।
আসসালামু আলাইকুম স্যার।
আসসালামু আলাইকুম।